I made Minecraft in Rust. Well, not at all yet, but at least my chunk generates way faster than my old version I did, and I think Minecraft does. And honestly, that is already a massive improvement. The first question you might ask is, yeah, another Minecraft clone in another programming language, really? Well, yeah, fair. But this project started as something much smaller. I wanted to learn Rust basics. I wanted to understand how rendering works on the GPU and build something visual instead of just working with console. And at some point I decided, okay, let's try a Minecraft like voxel engine. So here am I. I have made a few videos showing progress, but I skipped a lot of what I actually made. So in this one, I want to cover all I've missed, like how the project went from nothing to a Minecraft clone. But before that, we are going to skip the Vulkan tutorial. Base code, instant creation, validation layer, physical device selection, queue families, logical device, queues, windows, surface, swap chain, semantic views, graphical pipeline, shadowing modules, fixed function, render passes, swap chain recreation, vertex buffers, input description, stage buffers, index buffers, uniform buffers, descriptor set layout, descriptor purl, descriptor sets, texture images, samplers, depth buffering, 3D geometry, mip mapping, buffering, and as you can imagine, this part was slow, not only because Vulkan is verbose, but because I also had to learn mm, Rust from scratch at the same time. The Vulkan tutorial starts with hard-coded data. You give the GPU a few vertices and it draws a triangle or a rectangle. But a voxel world is not only hard-coded data. I need to turn a game concept into real renderable data and hopefully infinite. So the first question is, what are we actually drawing? A vertex is just a point with extra information, position, UVs, texture IDs, maybe lighting. A square is formed by two triangles. A cube is a six square placed in 3D perpendicularly. A chunk is a fixed block of world data, in my case 16 by 16 by 16 blocks. So the job is not draw Minecraft, the job is convert block data into vertices and indices that the GPU can draw. At first I took the most direct path, basically forcing chunks to exist, build geometry, upload it block by block and called it a day. And yeah, it worked for one chunk. In an early devlog I had a simple chunk running at something like 1000 FPS. Then I tried more chunks and suddenly the game dropped hard. I went from, yeah, this is fast, to why am I at 20 FPS with 9 chunks? That was the moment where Rust performance did not magically save me from bad architecture. The problem was not only one single thing, it was a pile of small mistakes. I was trying to update too much at once, lighting was too tightly coupled to the mesh generation, chunks were pushing too hard works straight into the renderer, there were no budgets, there were no workers, there was no real schedule, and the world generation and meshing were still too naive. So I started to replace the just do it now approach with an actual pipeline. Now chunks have a life cycle, it starts as requested, then the blocks are generated, then the light is processed, then the mesh is built, then the data is uploaded to the GPU, and only after that it becomes renderable. The important idea is that a block change does not immediately reveal the world, it marks consequences basically. This chunk needs lighting, this chunk needs a new mesh, this chunk needs GPU data. That could sound simple, well, but it changes everything. It means the frame does not have to pay the entire cost immediately. The next big piece is jobs. Generation and meshing can run outside the main thread, but workers do not touch the live world directly. Instead, the main thread creates a snapshot, basically a frozen copy of the chunk and its neighbors. The workers use that snapshot to build a mesh. When the result comes back, the main thread checks the version. If the chunk changed while the worker was busy, the result is old, so it gets ignored. This is one of those boring systems that prevents very annoying bugs. For rendering, I also stopped treating the world as one giant mesh. The renderer now works with chunk meshes. If one chunk changes, it uploads that chunk, not the entire scene. And even those uploads are budget. I only upload a small number of per frame, so a wave of finished chunks does not freeze the game. When there is lighting, originally lighting was stored directly in the vertices. That means if light changed, the mesh had to change too. That is painful for a voxel game, because light can change even when the visible geometry stays the same. So the engine is moving toward separating geometry from light. Chunks can have their own light data, and the shader can sample that data with drawing. The basic lighting idea is still simple. Basically, skylight and local light are packed into small value. The shader unpacks it, applies a small curve, and multiplies the block texture by the result, as I showed in other devlogs. But the important part is the pipeline. Lighting is its own stage, mesh generation is its own stage, and GPU upload is its own stage. Skylight also has to work across chunk borders. A light is not a tiny isolated world. If the chunk above blocks the sun, the lower chunk should know that. If a new neighbor chunk appears, border light and border meshes need to be marked as dirty. This is one of those parts that sounds obvious until you actually stream chunks dynamically. On the GPU side, replacing chunks also needs some care. If I replace a mesh buffer, I cannot just destroy the old buffer immediately while the GPU might still be using it. So all chunks buffers are retired and destroyed later after a few frames. Another big optimization is greedy meshing. Instead of rendering every single block face as its own quad, the mesher looks at a plane of visible faces and merges matching rectangles together. If 16 grass faces have the same textures and compatible lighting, they can become one big quad. That means fewer vertices, fewer indices, and less data to upload. There is a catch through you cannot merge everything blindly. Different lighting, different texture, or certain edges cases can create visual artifacts. T-junction are one of those things you start hearing about when you build a voxel mesher. In my case, the simple rule is merge only when the face data is compatible and split when lighting would become wrong. I also added camera side optimization. For example, raycasting is used for block selection. It works through the voxel grid using DDA, checks one block cell at a time until it hits something solid. And for rendering, I use flush-time cooling. It basically skips chunks outside the camera view. Important detail is that this does not upload the chunk from the world. It basically just avoids drawing it this frame. So if a chunk is behind the camera or outside the render radius, the renderer can ignore it and save the to draw that calls. So if a chunk is behind the camera or outside the render radius, the renderer can ignore it and save draw calls. The current frame pipeline is much healthier. Apply finishes job result, process something light, schedule more generation and meshing jobs, queue some light and mesh uploads, upload only a limited amount to the GPU, render what is ready and visible, and if there is too much backlog, the system slows down requests and drains the queues instead of trying to do everything instantly. That is the main difference between the old version and the new one. The old version asks, can I build this right now? And the new version, what is the next safe bit of work I can do this frame? This is why the game can now handle a much larger render distance without the same huge stutters. Now, is this a game yet? No. Right now it is still mostly blocks, flat world, the Bug UI, and only a lot of engine code. But the project is in a much more interesting place than before. It's not only can I draw chunks, it is not just can I draw a chunk anymore. It is starting to become can this engine stream a world, keep it lit, keep it responsive, and grow into something bigger. I don't know if I will keep the name Cubics, as I said before. I don't know how big this project will be. It is honestly pretty ambitious for me right now, but I want to keep pushing it, and I also want to explain more of the interesting parts as I build them. A lot of the ideas I looked into public voxel engine contents and devlogs, including people like Final for Each, Daniel P. Fox, GP Dev, Scars, and for example, and KV. Yeah, there is a lot of public knowledge around this stuff, and it helped me a lot. If you are interested, you can follow the project or join the Discord channel. Feedback is very welcome. Thank you for watching, and see you in the next one.